Previously, we showed how to calculate the mass of products from a given mass of reactants. In this video, we show how to calculate the mass of reactant required to completely react with a given mass of another reactant. We have already been presented with this scenario where we have 5.78 grams of butane, C4H10, undergoing a combustion reaction in the presence of oxygen to produce carbon dioxide and water. And we ended up calculating the mass of product, carbon dioxide, from the given mass of reactant. And the way we tackled this problem was via a three-step process. In step 1, we converted the mass of butane to moles of butane using the molar mass equation. In step 2, we used the moles of butane to calculate the moles of carbon dioxide using the ratio of the relevant stoichiometric coefficients. And in step 3, we converted the moles of carbon dioxide to mass of carbon dioxide by using the rearranged form of the molar mass equation. In this video, we're going to use a similar approach to calculate the mass of a reactant required to exactly react with a given mass of another reactant using the same butane combustion reaction. If we again say that we will start with, or we are given, 5.78 grams of butane, but this time we want to find or calculate the mass of oxygen required to completely react with this mass of butane, we will again see that we cannot do this calculation directly in a one-step process, going from mass of butane to mass of oxygen. Instead, we again need to refer back to this diagram where we can see that if we are given the mass of butane and asked to find the mass of oxygen, we have to take the same approach we just saw by firstly converting the mass of butane to moles of butane. Then we use the moles of butane to calculate the moles of oxygen by using the ratio of the stoichiometric coefficients in the balanced chemical equation. And then we calculate the mass of oxygen from the moles of oxygen using the rearranged form of the molar mass equation. So let's go ahead with step 1, calculating the moles of butane in 5.78 grams. Using the molar mass equation, we get the moles of butane equals the mass of butane divided by the molar mass of butane, which is equal to 5.78 grams, which is the information we've been given, divided by the molar mass of butane being 58.122 grams per mole, which we need to calculate separately by adding up the molar masses of the 4 carbon atoms and the 10 hydrogen atoms in the butane molecule. And that comes to 4 times 12.01 grams per mole plus 10 times 1.008 grams per mole. And remember, we get the individual molar mass values for carbon and hydrogen directly from the periodic table. And when we do this division in our calculator, we get 0.0994 moles of butane. In step 2, we now calculate the moles of oxygen that will be required by using this expression. Moles of oxygen equals 13 divided by 2 times the starting moles of butane that we just calculated. The 13 comes from the stoichiometric coefficient of the substance we are trying to find information about, in this case the stoichiometric coefficient of oxygen, divided by 2, the stoichiometric coefficient of the substance we've been given information about, in this case butane. So that will equal 13 divided by 2 times the 0.994 moles that we just calculated in step 1, which gives us 0.646 moles of oxygen required. In step 3, we now convert the moles of oxygen required into mass of oxygen using the rearranged version of the molar mass equation with mass as the subject of the equation. And so we have mass of oxygen equals moles of oxygen times the molar mass of oxygen. The moles of oxygen we just calculated in step 2 to be 0.646 moles, and we need to multiply that by the molar mass of oxygen, which is 32.00 grams per mole. And we get that number by doing our separate calculation of molar mass of the O2 molecule being 2 times the molar mass of a single oxygen atom, which is 2 times 16.00 grams per mole. And remember, we get the molar mass of a single oxygen atom directly from the periodic table. Multiplying these numbers together using our calculator, we end up with 20.7 grams of oxygen being required to react exactly with 5.78 grams of butane. In summary, we started with our 5.78 grams of butane. In step 1, we calculated the moles of butane and found that to be 0.0994 moles. In step 2, we used the ratio of the stoichiometric coefficients to calculate the moles of oxygen as 0.646 moles. And finally, in step 3, we converted the moles of oxygen to mass of oxygen by using the rearranged molar mass equation, and we found that to be 20.7 grams of oxygen. And that 3-step process is best summarized in a general sense using this diagram here, which we have now seen several times and is a very good guide to solving these types of stoichiometric calculations.